Hey there, and welcome to this explainer. I want you to go ahead, take a really deep breath, and just settle in. You've worked incredibly hard all year long, and now it's time for us to just sit together and walk through the beautiful, connected story of your chemistry curriculum one last time. We're going to go through every vital detail, literally from the way electrons spin all the way to how life-saving medicines are built so that you can walk right into that exam room with absolute, total confidence.
You've put in the hours, you've memorized the formulas, and trust me, you know this material. Today is really just about tying all those loose ends together. We're going to map out the entire narrative so that when you sit down for your exam, everything just flows naturally.
So, here's our game plan for today. First, we'll look at the first transition series. Second, we'll cover their properties and that weird little nickel glitch. Third, we'll dive into iron extraction and alloys. And fourth, we'll wrap up with qualitative analysis, which is basically our chemical detective work.
All right, let's get right into it with Part 1, the first transition series.
To really understand why some metals form the backbone of our bridges and others power our batteries, we have to begin at the very heart of the periodic table. The first transition series gives us 10 metals, starting at scandium, element 21, and ending at zinc, element 30. What makes these guys so special is that we're slowly filling up their 3D sublevels with electrons. And why does that matter? Well, an atom's happiness or its stability depends entirely on that sublevel. They want that D sublevel to be either completely empty, exactly half-filled, or totally full. But keep this trick in your back pocket for the exam. Zinc is not technically a transition element. Why? Because its 3D level is always completely full, even when it forms an ion.
Okay, let's dive into a really fascinating anomaly here. Because of this powerful, intense drive for stability I just mentioned, chromium and copper actually break the normal rules of electronic configuration. Seriously, instead of filling the 4s level normally, they actually pull an electron from the 4s level into the 3d level just to achieve that perfect half-filled or totally full state.
Now, when these metals react, they follow a very strict order of operations. They always lose their outermost electrons first, which means the 4s sublevel empties before the 3d sublevel. And here's a good rule of thumb. Their oxidation states usually won't exceed their group number. But of course, there's an exception. Watch out for group 1b, the coinage metals, so copper, silver, and gold. Their oxidation states absolutely can go higher than their group number.
Moving right along to Part 2, Properties and the Nickel Glitch.
Because this internal electronic structure is so unique, it gives these metals some pretty wild physical properties. Generally, as you move across the series from left to right, the atomic mass steadily increases. But look at this famous glitch right at nickel. The mass actually dips down, making it lower than cobalt. This happens because nickel has 5 stable isotopes, and when you average them all out, it pulls the overall atomic mass down to 58.7.
Now, what's really interesting on this slide is how the atomic radius behaves. From chromium to copper, the radius stays almost perfectly constant. It's like a tug of war that ends in a tie. As you add protons, the pull of the nucleus increases, trying to shrink the atom. But at the exact same time, the new electrons being added to the 3D sublevel are repelling each other, pushing outward. These two forces balance each other out perfectly. This stability is exactly why these transition metals make the absolute best catalysts in the world. Their stable electron clouds hold on to reactants and massively lower the activation energy needed to kick off reaction.
And you can literally witness this electronic behavior with your own eyes. Elements are paramagnetic when they have unpaired electrons. Those lonely electrons spin and create tiny magnetic fields, meaning the metal is actually attracted to magnets. On the flip side, if all the electrons are neatly paired up, they cancel each other's spin out. This makes the element diamagnetic, meaning it's actually slightly repelled by magnets.
You can even calculate the exact magnetic moment of an ion using this specific formula, where n is just the number of unpaired electrons. Oh, and this unique structure, it gives these metals their brilliant colors. A chromium-3 salt will always look green to you because it absorbs specific light and reflects the complementary color based on the classic Grog movie code. Understanding all these properties explains why these metals are so vital to our world. It's why scandium makes MiG fighter jets light and strong. It's why titanium, our space grandma metal, is used for artificial joints because the body doesn't reject it. Think of vanadium in car springs, manganese making real tracks stronger than steel, or cobalt-60 literally treating cancer by emitting gamma rays.
Okay, Part 3, Iron Extraction and Alloys. We have to talk about the true star of the series, iron. Iron is so fundamentally essential to human industry that we need to know exactly how to pull it from the earth. It's not just sitting around pure, it's locked in ores.
We're talking about red hematite, yellow limonite, and the highly magnetic black magnetite.
The journey from rock to steel is this incredibly satisfying problem-solution narrative. First up is dressing, where we crush, sinter, and roast the ore to drive off moisture and impurities. Then we hit reduction, where we strip away the oxygen. We do this in either a blast furnace using carbon monoxide or a midrex furnace using water gas. Finally, we take that purified iron and move right into steelmaking.
Because pure iron is way too soft, the crucial step is mixing it into alloys. We can create an interstitial alloy by tucking tiny carbon atoms into the gaps of the iron lattice to make it super hard. Or we make a substitutional alloy by swapping iron atoms out for atoms of a similar size, like chromium, which gives us perfectly rust-proof stainless steel.
Sometimes elements actually combine chemically to form an intermetallic alloy, like cementite, which just totally ignores normal valence laws. Now, remember your iron map reactions for the exam. Iron reacts with oxygen or water at 500 degrees to form magnetite. It reacts with chlorine to give iron 3 chloride. It'll party with concentrated sulfuric acid to give a mix of iron 2 and iron 3 salts. But it becomes completely passive, meaning it stops reacting entirely when it meets concentrated nitric acid.
Finally, Part 4. Qualitative analysis. Detective work.
Since iron and its transition metal buddies are so essential but almost always found mixed up with other stuff in nature, chemists needed a reliable way to identify them. Qualitative analysis is pure detective work. We use chemical reagents to hunt down hidden ions, based on one golden rule. A more stable acid will always replace a less stable acid in its salt.
Let's meet our first detective squad. Dilute hydrochloric acid is perfectly suited to hunt down 6 specific thief anions of very low stability. When HCl kicks them out, it creates highly noticeable reactions. Carbonates will violently bubble with carbon dioxide. And if you have a sulfide, you'll know immediately because it releases a gas that famously smells exactly like rotten eggs.
But just getting a smell or a bubble isn't quite enough for a chemist. We need proof. Once our reagent gets a lead, we always rely on specific, confirmatory tests to lock in the identity of the hidden ions. If you suspect a sulfide, you add silver nitrate, and bam, you get a distinct, undeniable black precipitate of silver sulfide. We never guess, we prove.
And there you have it, the whole beautiful connected story. From the strange behavior of the 3D sublevel to the massive blast furnaces, all the way to the meticulous detective work of chemical analysis. You have the entire roadmap in your head now. You know the rules, you know the exceptions, and you know exactly how this applies to the real world. So take one more deep breath, trust in your preparation, walk into that exam room with total confidence, and ask yourself, what amazing things will you conquer next? You've got this. Good luck.